Kia ora and welcome to this video on question 3 of the 2017 Scholl Calc exam. All three questions are set in a differentiation context. First problem involves us using logs to differentiate an expression where x is in the power. The second part involves the product rule over and over again, and part C introduces hyperbolic functions and their derivatives. Also, we need to find the derivative of an inverse function, and we're going to look at three different ways of solving that problem, including one that's not in the NCA mark schedule. Did I say NCA? I meant scholarship. Like a really, really wicked way to solving that problem. So hopefully you enjoy it. Okay, part A. We've got a function x to the power of x to the power of x, and they've given us brackets there just so that we know what way the powers work. So we've got y equals x all to the power of x to the power of x, and we need to find dy dx. The first thing to note is that the power rule that you've learned, like for example x to the 5 diffs to 5x to the 4, only works when the power is a constant. So it could be fractional, it could be decimal valued, but we can't do it when it's x to the x. So if I have something like x to the x, I don't diff that to x times x to the x minus 1. Okay, that's completely wrong. The question hints, it says use any valid algebraic technique such as implicit differentiation and logarithms. So if I log both sides of this expression, so ln y, use the natural log because I know what its derivative is, and ln x to the power of x to the power of x. Now I can bring this power down the front using basic log rules. And like at this stage, I could implicitly differentiate, or I could take logs again. But I'm just going to differentiate at this point. So if I took logs again, it would look like this, and then I've got log of x to the x times ln x, and I can use the log of a times b rule to split this into log of x to the x plus log of x, and then I can do the same thing and bring the power down. But that is unnecessary to actually do it that way, although it would work. At this point in time, I'm just going to differentiate the whole expression implicitly. So the left-hand side, because we're diffing with respect to x, I write that as 1 over y times dy dx. And the right-hand side is a product. So if I call this f and I call this g, then I'm going to use f dash g plus g dash f to diff it. And on this, sort of in the margin, I need to work out what f dash is, because if f is equal to x to the x, that derivative is not on the formula sheet. So I do a little bit of side work on this. If y equals x to the x, then ln y is equal to ln of x to the x. I can bring the x down. This is kind of what I was going to do anyways with the suggesting using logs again. So I've got x ln x, and then I can use implicit differentiation on this, and again it's a product. Okay, it's like a u there and a v there, so to diff it, it's u dash v plus v dash u. Derivative of x is 1 times log x, derivative of log x is 1 over x times x, therefore dy dx is equal to, I need to bring the y up the top right, okay, times both sides by y, so y multiplied by ln x plus 1, because 1 over x times x is 1, and then y for this one was x to the x. Okay, so all of that work is just to find the derivative of x to the x. Okay, x to the x differentiates to this dude. Okay, so that's my f dash. So I'm going to move this a little bit down. So therefore 1 over y dy dx is equal to f dash, or f was x to the x, so f dash is this stuff I've just derived, multiplied by g plus g dash multiplied by f. And again, multiplying both sides by y, we've got y multiplied by all this stuff, and x to the x times 1 over x is x to the power of x minus 1. X to the power of x divided by x to the power of 1. And in this case, y was the original function, x to the power of x to the power of x. So just remember that, I'm not going to rewrite it out again, but x to the power of x to the power of x. Okay, and then it said evaluate this expression when x is equal to 2. Okay, so when x equals 2, dy dx equals 2 to the power of 2 squared, so 2 to the power of 4, which is 16, multiplied by 2 squared, so 4, times ln2 plus 1. I'm just going to evaluate that as a decimal because it's not going to be a nice number. 1.6931 times by ln2. It's got to be careful of where brackets are in this. Plus 2 to the power of 1. 2 to the power of 2 minus 1. Okay, and then if I evaluate all that stuff, I've got 4 times 1.6931 times 0.6931 plus 2, all times by 16, gives me 107.1 to 1 decimal place. There's a bit of rounding involved there. Okay, so that's how you differentiate x to the power of x, and it's also how you differentiate x to the power of x to the power of x. Second question, got 3 parts to it. Scaffolded, so that enables you to find the derivative, find the second derivative, and then generalize a pattern. So we've got e to the x sine x, and we need to prove that it equals root 2 e to the x sine of x plus pi over 4. Okay, so use the product rule first. So dy dx, we diff the first thing, e to the x times the second, then diff the second thing and times by the first, and then we can write this as e to the x all times sine x plus cos x. Now that's not the format that the proof needs us to, or like if we want to prove this we need to put it into this format, and there's 2 ways about going about this. We know that we've got the e to the x, but we haven't got the root 2 sine x plus pi over 4. So I could fudge it, and I could have a look at what is root 2 times sine of x plus pi over 4 equal. And that's a compound angle formula. It's sine of a plus b. So I could write that as root 2 sine of x cos of pi over 4 plus cos of x sine of pi over 4. I'm using a trig identity there. And then cos pi over 4 is 1 over root 2. And sine pi over 4 is 1 over root 2. And those both cancel with the root 2. So we get that equals that, which equals just sine of x plus cos x. And I can do that because that cancels with that and that. And then I would just backtrack it and go, therefore dy dx equals e to the x times root 2 sine of x plus pi over 4. Okay, but I can only do that if the answer is given in the question, because I can just expand the answer and get to where I am after the first step. If you didn't have that and you were wanting to write it in terms of just sine rather than sine x plus cos x, you could learn about these things called linear combinations. I'm just going to do this on the side. Linear combinations of trig functions. So if you have two trig functions, for example, you might have a sine x and b cos x, where the period of these are the same. So it's not like sine 2x plus cos x. It's both of these trig functions have the same period. In this case, they both have a period of 2 pi, but they could have different amplitudes. When you add these things together, you get one trig function. I'll just show you that on Desmos. This is me preparing for an earlier thing, so I'll just hide that for now. If we got something like y equals two sine of x, for example, and I might have y equals, actually I'm going to call this one f, this one g, and I say cos x. So take two trig functions, and if I add them, okay, so at the moment those trig functions are out of phase, but they have got the same period. When I add them, see how I just get a trig graph which actually has the same period. It has a period of 2 pi. So when you add two trig functions, the amplitude's different, of course, and the position where the first maximum occurs isn't at an obvious place, but the period remains the same. So with that information, we can take a sine x plus b cos x, and this adds to some new amplitude of, and you can choose either sine or cos, but cos of x minus alpha. So there's textbooks that talk about this. There's linear combinations of trig functions. And when we expand this out using the compound angle formula, we get cos x cos alpha plus sine x sine alpha. And then we can look at how on the right hand side we've got two trig functions. We've got a cos x and a sine x, and if we equate the coefficients of it, alpha is just a number that relates to the shift. So r cos alpha is equal to b, and r sine alpha is equal to a. That gives us a simultaneous equation, and we can divide these equations here to get sine alpha over cos alpha, which is tan alpha, equals a over b, and we can get the r value by subbing back into one of the equations. So, okay, where's this coming from? Let's go back to the specific problem, and we were at sine x plus cos x, and we were just saying, like, what does sine x plus cos x actually equal? And this is assuming we don't have the answer to the problem. So, okay, so I could go sine x plus cos x. I know when I add these two trig functions, I get a different trig graph. I get r times, and this time I'm going to use sine of x minus alpha, because I want to put it into a sine format for this particular answer, but I could have used cosine. I expand out the right hand side using the compound angle formula. Sine x cos alpha minus, oopsies, it's a sine x cos alpha minus cos x sine alpha, And then I do the same thing as before. I go, okay, the left-hand side's got sine x, so r cos alpha must equal 1. And the right-hand side has also got a minus sine alpha with an r. Minus r sine alpha is going to equal 1 because the left-hand side's just cos x. And if I divide these equations, it gives me negative tan alpha equals 1, or tan alpha equals negative 1. So if I take the tan inverse of negative 1, it gives me minus pi over 4. Okay, there are multiple solutions to this, but I actually want that one. Alpha is minus pi over 4. And then if I sub that alpha value back into one of the equations I had, well, let's go with r cos alpha equals 1. So if I sub in alpha as minus pi over 4 into that, cos of minus pi over 4 is, making sure I'm in radians on my calculator, is 1 over root 2. So r must equal root 2. And then I can go back to this structure here and go sine x plus cos x equals root 2 sine of x minus alpha, and remember alpha was negative, so it's x plus pi over 4. And then that goes back up into where sine x plus cos x is, and that's root 2 sine of x plus pi over 4. Okay, so that's a little bit of a tangent here to looking at a different way of solving the problem, but of course when it gave you the answer to it, you're just formatting it in that answer, and it was easier to expand the answer and compare. Okay, the second part of this question asks us to find the second derivative in terms of exponentials and sine functions only. So we've got a couple of options here. We either differentiate from this point, because it's fairly easy to do so, or we differentiate from the final point, which is already in that structure. And that's the way I'm going to do it. Okay, so notice that there's a root 2 in there. That just sits in the front. So every time we differentiate, we're going to get another root 2. And we've got e to the x times sine of x plus pi over 4, which is very similar to the original function, which was e to the x sine of x. Okay, so it's about spotting patterns in this problem. Okay, so d squared y over dx squared, the second derivative. Root 2 is going to sit there. Then we need to diff e to the x times by sine of x plus pi over 4. I'm going to use the product rule again. So diff the e to the x times by sine of x plus pi over 4. Then diff the sine of x plus pi over 4. And times by the e to the x. Then pull the e to the x out the front. Sine of x plus pi over 4 plus cos of x plus pi over 4. Now, rather than go through the whole rigmarole of doing that combination thing again, we've got sine of something plus cos of something, and we had that before. We had sine of x plus cos of x, except instead of x, we've got x plus pi over 4. So going from here down to there, replace the x of x plus pi over 4 means that the bottom result will be x plus pi over 4 plus pi over 4. So it'll be x plus pi over 2. Okay, so this is going to be root 2 e to the x, and then this stuff is going to be root 2 sine of x plus pi over 2. The root 2's stack up, so we get root 2 squared, which is 2 of course. E to the x just sits there, and then we get sine of x plus pi over 2. Okay, so in general, if we did that again, it would just happen the same way, because the root 2, we would just get another root 2 e to the x. We wouldn't get any extra e to the x, and we'd just shift that sign graph again. The third part says to find an expression for the nth derivative. So similarly, d squared y, oopsies, not the second derivative now, the nth derivative, dny over dxn is equal to root 2 to the n e to the x sine of x plus n pi over 4. Okay, and then it says to evaluate this thing when x was equal to 0. So the nth derivative, root 2 to the n, which can be written as 2 to the n over 2 if you wanted to. E to the 0 is 1, so that term will just, we don't need to write it. And then sine of, if x is 0, we get sine of n pi over 4. Okay, and like that is the answer to the problem. But because we've got n being, where n is a whole number, we're talking about derivatives here. So we're not talking about fractional derivatives and fractional calculus, although that is a very interesting area of mathematics if you want to Google it. We're just talking about where it's first derivative, second derivative, and so on. These things sort of bounce around because of the sine function repeating. So you can evaluate that further by knowing that, for example, if n equals 1, sine of pi over 4 is equal to root 2, sorry, my bad, 1 over root 2, n equals 2, we've got sine of pi over 2, which is 1, n is 3, we've got sine of 3 pi over 4, which is also 1 over root 2, n equals 4, we've got sine of pi, which is 0, and it kind of repeats like that. So we could explore what happens, and the mark schedule does, but I believe that this answer here is perfectly acceptable. Okay, last question, and I did say we're going to look at this in 3 different ways, so the video is possibly getting a little bit long here. But the first up, we've got these hyperbolic functions, and if you've never seen them before, they are trigonometric in their nature, but they're defined in terms of exponentials here, in terms of Euler's number. So if you were like, oh, what the heck's that SINH thing mean? It's actually pronounced shine, the shine of x. Well, that is the function. It's a half of e to the x minus e to the minus x. And the other one, cosh, there's also hyperbolic tan, which is pronounced than, even though it looks like tanch. And this one looks like cinch. But those are how they're defined. They're defined in terms of e to the power of x. And then the question says we need to find the derivative of the inverse function. So another little thing is to say that this is not equal to 1 over the hyperbolic sine. We're looking at a functional inverse. Functional inverse rather than a multiplicative inverse. Now you've seen these before, you've seen inverse functions before, because if you had, for example, in year 11 trig, you had an angle theta, and you would, I don't know, given that this was 5 and this was 8, to find the angle theta you would go, no, you wouldn't go cos, you would go tan of theta is 5 over 8, and then to find theta you would find the inverse tan of 5 over 8. Okay, so that it didn't mean 1 over tan, it's the inverse function. But this can be misleading, because if I write sine squared of x, I actually mean sine of x all squared. And if I say sine cubed of x, I actually mean sine of x all cubed. But when I say sine to the negative 1x, I don't mean sine x to the minus 1. What if I wanted 1 over sine of x? Well, of course we know that 1 over sine of x is the reciprocal of sine of x, which is cosec. It's got its own name. And the inverse sine function is arc sine, but this one here is the inverse hyperbolic function. Okay, let's have a look at my stuff that I've got here. Get rid of those ones. Inverse functions are really easy to deal with. Like y equals 2x is saying take x and multiply by 2. The opposite function of that is take x and divide by 2. So you get a symmetry here where all of the coordinates, for example, on this bottom graph we've got a coordinate of 2, 1. On the inverse function we've got a coordinate of 1, 2, as you can see. Okay, so all the coordinates are just mirror images of one another, x and y interchange. Another inverse function, y equals x squared and y equals square root x, are only inverse functions when x is positive, because the square root of x is not defined when x is negative. But you get that mirror image in the line y equals x. Sine of x and arc sine of x also have inverse functions, but only on a restricted domain. Because if we look at that arc sine graph there, it would bend back around and then we'd have two y values for a particular x, and that's a bit of a problem. That would no longer be a function. So we have to restrict the domain of the sine graph to be able to find the inverse function arc sine. Okay, but that's how inverse functions work. They're just, the x and y values just interchanged. So with that knowledge in mind, if we look at finding the inverse hyperbolic function of sine differentiated, so I've got y equals the hyperbolic sine of x. Okay, now we're told in the question that the hyperbolic sine of x is a half e to the x minus e to the minus x. So we could actually differentiate this. And the question says differentiate the inverse function, but let's just have a look at what we get when we differentiate this. dy dx is equal to, it turns out it's equal to cosh of x, but you might not know that. So we diff the right hand side. The half stays there, e to the x diffs to e to the x, minus e to the minus x diffs to plus e to the minus x, and voila, there is cosh of x. So just like when you differentiate sine and it goes to cosine, the hyperbolic sine differentiates to the hyperbolic cosine. What about cosh? Cosh of x is a half e to the x plus e to the minus x, and when we diff that, the half stays there, e to the x stays there, plus e to the minus x diffs to that, and that there is the hyperbolic sine function. So unlike in trig, when you diff cosine and it goes to minus sine, for hyperbolics, the derivative of the hyperbolic cosine is just the derivative of the hyperbolic sine, so they're opposites of one another. Now these things are all preliminary results, okay? They're just to help us explore this, and we might use them in the methods later on. Okay, the other thing is, when you have a trig identity, one of the most basic trig identities we know is sine squared plus cos squared equals 1. That's true for all x. Let's have a look at what the hyperbolic trig functions do. If I take sine of x and square it, okay, so I want to square this dude. Squaring that will give me a quarter. E to the x minus e to the minus x all squared to binomial. So I've got e to the 2x, or e to the x squared, plus e to the minus x all squared. And then we've got two lots of e to the x times negative e to the minus x, which is minus 2. Hyperbolic cosine, or cosh squared, I get, now I'm going to diff this one. No, not diff it, my bad, I'm just going to square it. A quarter, I get e to the 2x plus e to the minus 2x, but at this time I get plus 2. Okay. And when I add them, I don't get any simplification, but when I subtract them, if I go cosh squared x minus sine squared x, all the terms cancel. My bad, not those ones. Those terms will cancel if I subtract, except I get 2 minus negative 2, all divided by 4, so I get 1. So the trig identity for sine and cosine is sine squared plus cosine squared equals 1. For hyperbolics, it's cosh squared minus sine squared equals 1. Okay, so that's going to be another useful result. And it's the sort of stuff that you can explore at scholarship level. You can try out different things to see how they relate. It's an unfamiliar context, for unless you'd seen them before the exam, it would be unfamiliar, but that's how you play around with it. Okay, now for the differentiation. Method 1. Okay, we start off with y equals sine of x, and we know that that equals a half e to the x minus e to the minus x. The inverse function is literally x equals a half e to the y minus e to the minus y. Okay, in other words, y in this case is equal to the inverse hyperbolic sine function. Okay, now I could make y the subject of that. If I did that, I would have the inverse function. But written as this, I can implicitly differentiate. I can find dx dy. A half e to the y plus e to the minus y. And that is equal to cosh of y. So dy dx, which is the thing I wanted to find, and bear in mind that, y is equal to the inverse sine function now, because I switched them around. Okay, at this point here, I switched the letters around. So dy dx is actually the thing I want to find. Well, that's going to be equal to 1 over cosh of y. And then I use the trig identity that I've developed up here to relate these things together. Cosh, and remember that's got x's in it. But if I rearrange that for cosh, I'm going to get the square root of 1 plus sine squared of y, which is sine of y all squared. But y is equal to the inverse sine, so the sine of y is equal to x. Okay, because they're opposites of one another, which means that we've got 1 over root 1 plus x squared, which is the proof done. Okay, and all I did there is switch the letters, differentiate, and then get rid of the y's by relating them to the x's. That's method 1. Okay, method 2. I'm sure there's more than 3 methods, but these are the ones I came up with. Is actually to find the inverse function. So at the point where I switch the letters, if I make y the subject of this, so the first thing I do is times by 2 both sides. And realize that e to the minus y is 1 over e to the y. If I times the whole equation here through by e to the y, I end up with a quadratic equation in e to the y. So I can solve that using the quadratic formula. Minus b is 2x plus or minus, the b squared is minus 2x all squared. Minus 4ac is plus 4 all divided by 2. 2x over 2, and then I pull a 4 out of the square root. When I do that, it becomes a 2, and that knocks off the denominator 2. And then I've got y is ln of x. I choose between plus or minus. If I take the minus there, I'm going to end up with x minus root x plus x squared plus 1. X squared plus 1 is bigger than x squared. So root x squared plus 1 is going to be something bigger than x. And then I'm going to take it away from x and get a negative number. So the log of that would not be defined. So I take the plus. Okay, and now I differentiate this, because this is the inverse function. Okay, so the original function was in terms of e to the x. The inverse function, no surprises, is in terms of log. So if I diff this, I know how to diff log, it's just 1 over. But then I times by the inner derivative, which is 1 plus x squared plus 1 to the half diffs to half x squared plus 1 to the minus a half times by 2x. Now this looks like nothing like the proof that I'm trying to achieve, but if I tidy it up, things fall out really nicely. Because I can write this bracket as 1 plus 2's cancel, get x on the top, divided by root x squared plus 1. I can then put these fractions together. I can add the 1 and the x over root x squared plus 1 together by making it a common denominator. Root x squared plus 1 plus x all over root x squared plus 1. And then, lo and behold, that cancels with that factor, and we end up with the proof. Now that's a bit more tedious because in this question, in this method, we had to find the inverse function before we differentiated it. But that technique works for any inverse function. If you take a function and you switch out the letters and then make y the subject of it, you'll have the inverse function. Okay, now method 3 is something I was playing around with just before making this video, and I think it's a really good way of doing this problem because it tests your understanding of what inverse functions actually are. An inverse function is the opposite of the function that it's the inverse of. So for example, if I took 2x and x over 2, these are inverse functions. Because what happens if I put in the number x and I double it, I get 2x, and then if I put that into the other function, I get back to x. So starting with x, using both functions, I should arrive back where I started. Try that for something like x plus 3 and x minus 3. They're the opposite functions. If I take x and I plus 3, I get x plus 3. If I then take that and minus 3, I get back to x. Okay, so inverse functions are nothing special really, they just do the opposite and get you back where you started. So with that knowledge, I've got the hyperbolic sine function. If I substitute the inverse hyperbolic sine function into it, I should get x. And now I could differentiate these things implicitly because I've already worked out that the derivative of the hyperbolic sine function diffs to the hyperbolic cosine function. We've got a composite function here. We've got the chain rule needs to work. So we diff the outer function. Diff that will be cosh of the inner function. Multiplied by the inner derivative, which we don't know because that's actually the thing we're trying to find. And the right hand side diffs to 1. Okay, so this is the thing we're trying to find. So make that the subject of the formula. Equals 1 over cosh of inverse sine, and that's actually the answer to the problem, but we need to prove that it equals to 1 over root 1 plus x squared, and that's where we bring in our trig identity. This one in yellow, cosh squared minus sine squared equals 1. So using that, the derivative of the inverse function is equal to 1 over, rather than cosh, I'm going to use 1 plus sine squared square rooted. Okay, I'm going to rearrange this as cosh of x equals the square root of 1 plus sine x all squared. But it's not cosh of x, right? It's cosh of sine of x. So wherever there's a x, I'm going to write sine of x. So So I've got root 1 plus sine of sine inverse squared. And sine of sine inverse is x, so I get 1 over root 1 plus x squared. Okay, that was a little bit subtle there what I did, but look, I used the identity to write cosh in terms of sine, and then instead of cosh of x I wrote cosh of sine of inverse of x. So I've replaced this x in here with that, and then those are inverse functions, so I get x. How cool. Apologies for the long video, but hopefully you've learnt heaps, and we'll see you next time.